Hello everyone. Let me check my sound levels and looks good. All right. Well, let's start. Maybe I should tell you a little bit about the test. Um, I've written it already. It's 28 questions long, and I haven't gone through it in a lot of detail. So maybe I'll change my mind about that. I'll tell you for sure on Wednesday. But if I take out, it'll be one or two questions less or more, but about 28 questions. Nonetheless, I time these things very carefully, and it should take you about 1 hour to do the test, but I'll give you 2 hours to do it, as I said in my email. And you should just do it during your regular class time. However, if you have a conflict and things aren't going to work out for you where you can get the full 2 hours, then just email me, and what I can do is I can start it earlier, and no matter when you start it, you get the full 2 hours, so we can work around that. It covers Newtonian mechanics, so Newton's laws and solving problems with Newton's laws, which is what I'm going to do today. I'm going to do a problem on that, and it'll be also Newton's universal gravitational law and Kepler's law, okay, and also the conservation of energy, which is the last topic we did, okay. So I'll give you a few more details on Wednesday, but I think that's pretty much done. Okay, so let's start. Today I have just one question in three parts, and I didn't write it out fully in English here. Rather, what I did is I drew it. So let's take a look at the drawing here. What we have is two inclined planes, okay, and usually we did like one inclined plane and the other one was a dangling mass, but this time I've got two inclined planes there, and I've got a 7 kilogram mass at 40 degrees and this 10 kilogram mass at 30 degrees. And just to be clear here, let's call the 7 kilogram M1. Oh, that's weird. 1 second, my cursor's not working right. Oh no! And I've lost this is very strange. Guys, I'm sorry, I'm having some technical difficulties. Let me see if I can fix this. And all right, so you're seeing a blank screen right now, but that should disappear in just a second while I bring that program up again. I have no idea what happened there. I hope this doesn't become a problem uh, because I kind of need that program. All right, let me see here. M1. Oh yeah, okay, now it's working. I don't know what happened there. M2. Let me see if you're. Oh no, it happened again. Oh, it was a delay. Okay. I hope this is. And I lost it. Oh no. All right, give me just a second. We'll try it one more time. Is that appearing? Okay, that appeared. Let me see if I can draw on it now. This has never given me a problem before. And it crashed again. I'm having difficulties with that program crashing. So let me see if I can try this a slightly different way. Uh, if not, I do have a kind of a fallback, but I don't want to fall back on this other approach here. Okay, you could see it here. All right, let me bring up the diagram. There it is. Okay, so what I'm going to do is, it seems that the program crashes whenever I draw stuff. So what I'm going to do is I'm going to describe the what I'm going to do, how you would do this. And if you do, you need to actually see me going through the drawing of it. There is the other video, but I think we can. I think I can move ahead with this at least partially. Okay, so what we have here is a 7 kilogram mass on a 40-degree incline and a 10 kilogram on a 30-degree. And my first question is, what's the acceleration? Okay, now I'm going to try to draw. If it crashes again, well then that'll be it. But the first thing you need to do is resolve the gravity. It's going to crash. There it goes. Wow, I did not expect this. I did not expect this. Okay. All right. Okay. 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 And it worked just fine this morning. So let me see if I can maybe, if instead of doing that, maybe if I just start drawing from scratch here. Okay. All right. Is that going to work? All right. You know what? If I seem to draw from scratch here, this seems to be okay. So let's make this 40 degrees. Let's make this 30 degrees. I think I see what the problem was. Okay. And there was a 7 kilogram mass over here. And there was a 10 kilogram mass here like that, and they were attached by a string like that. And that's terrible. Okay, good enough. 7 kilograms here. I think I can work with this. Okay. It seems to be that whenever I started with that other diagram first, and then I was drawing, that's when I got into trouble. All right, we could do this. We can continue like this. Okay, so there's no friction to start with, and I want you to figure out what the acceleration is of the system. Okay, so the first thing you do is, isolate the two masses and draw a free body diagram for each one of them. Okay, so we'll start with the 7 kilogram here, and there's a force this way and a force that way, like that. Well, two components of the gravitational force. This one here, if we call this one M1, and we call that one M2, like that. All right. This one is M1G, and the perpendicular component, and this is where a lot of students make a mistake, the perpendicular component is cosine, and then the angle is 40 degrees. Okay. And this component here is M1G sine of 40 degrees, like that. Okay, and since we're at it, we can do it here too. But I won't actually write down the mg2 cosine and mg sine, because I think you know how they're calculated. But this is basically these are the two components of gravity: the perpendicular and the parallel component. Okay. Now you ask yourself, okay, so that's gravity acting on those two forces. Sorry, on those two masses. What other forces are there? Well, there's the normal force like this, and I'll call this one Fn1. Okay, and the reason I've got a subscript 1 there, it is a normal force, but I'll put a 1 there because it is the normal force for the 7 kilogram. Okay, and then over here, this will be F N2 like that. All right. And that's the normal force for number 2. And then is there another force on them? Yeah. There's the tension up here like this. All right. Ft like this. And you have another tension up this way like that. And it's the same force Ft. Okay, the reason it's the same force is because of Newton's third law. So Newton's third law will say that this force here is equal in magnitude to that force. It would be opposite, except that the pulley there is actually what's changing the direction. Okay, otherwise, if you've got like a tug of war where two objects are pulling on one another through a rope, then the forces would be equal in magnitude, opposite in direction, but the pulley is changing the direction of Ft. Nonetheless, the magnitudes of Ft, that is, whatever that turns out to be in newtons and whatever that turns out to be in newtons, that they'll be the same. Okay, so there are the forces acting on the two masses. Okay, and to start with, for question number 1, there is no friction. All right, so let me see if there's any questions in the chat. Okay, apologize for the technical difficulties there, but I think I know what was happening when I was starting with the pre-drawn diagram. That's when it was crashing. Okay, and well, this one's a little bit messier, but I think you can see what's going on. Okay, so let me switch now to the whiteboard here, and let's start answering the question. So what's the acceleration of that system? All right, and what's the direction of the acceleration, and also what's the tension in the rope, assuming no friction. So assuming no friction, let me just show you this again. Each one of the forces has, each one of the masses has 3 forces on them, and then gravity, you split them up into a parallel and perpendicular. Okay, and don't forget the perpendicular is the cosine and the parallel is the sine. Okay, and yeah, that looks, the writing there is pretty pretty bad, but I think you can see that this is m1g cosine 40 degrees, and the other one's mg sine 40 degrees. Okay, I didn't put the formulas there, but I'll do that in a second for the 10 kilogram. The other thing, actually, before I switch back, is that that the normal force here is going to be canceling the that force down there, the perpendicular component for both of them. So that will also cancel that one like that. Okay, so we really, when there's no friction, we really don't even have to worry about the normal force of the perpendicular component of gravity. All we have to really worry about is this one here, that force there, and this one here. Okay, so let's work those out. All right, so let me just cut and paste so that I don't make a mistake here. All right. All right. So for the 7 kilogram, the parallel component of gravity, okay, like I said, we don't need the perpendicular component because that's going to cancel against the normal force. All right. The parallel component of gravity, that's m1 for the 7 kilogram mass. That's m1g sine theta. M1 is 7 kilograms. G will round off to 10, and the sine of the angle. So that was the angle for the 7 kilogram. That was 40 degrees. Sine of 40 degrees. Work that out, and it turns out to be 45 newtons. Okay, so just quickly switch back to that diagram. Yeah, actually, I can write that in here. Down here, this one down here, that's equal to 40 newtons down here like that. Okay. All right, let's calculate what this one is. All right, so that one is. We'll finish it off in the other the 7 kilogram in a second, but that one is the 10 kilogram is m2g sine theta, which is 9 times 10 times the sine of 30 degrees, and that turns out to be 50 newtons. Okay, so this one over here is actually 50 newtons like that. Okay, so we have 45. Sorry, I wrote 40 newtons here. That's incorrect. Hold on. That's 45 newtons. And this one is 50 newtons. Okay, got it right now. Okay. All right. So 45 newtons and 50 newtons. All right, let's switch back here. And now that we've got those two forces, let's work out the net force on the 7 kilogram mass. So the net force, remember, is we add up all the forces on it. And there's only 2 forces that you really have to consider because, like I said, the other 2 will cancel. So for the 7 kilogram mass, Fn1 That's canceling the perpendicular component of gravity. Okay, so those two are out of the picture. There's 45 newtons downhill, and there's this unknown force uphill, Ft, and you wonder which one's going to win. Okay, is this thing going to accelerate downhill? Like, is it going to accelerate this way? In which case, this one would accelerate up like that. Okay, or is it going to accelerate uphill? Okay, in which case this one will accelerate downhill. Well, if you're not sure, you can always just pick a direction and then you'll get a negative for the acceleration afterwards. But you actually do know what it's going to be. And if you just take a look here, these two tensions are the same. They're an internal force. So, for the purposes of this kind of an analysis, you could just ignore them for a second. You could think about gravity pulling 45 newtons this way and 50 newtons that way. Okay, and if you think about it, this is kind of like the Atwood's machine, which is actually you should have done in the lab, and or will do in the lab. I'm not sure if you've done it already, but that means that the 10 kilogram is going to be sliding downhill, and it'll drag the 7 kilogram uphill, and so the acceleration actually will turn out to be this way. Now, if you can't figure that out, like you can't intuitively see that, that's okay. If you just go ahead and like assume a direction, then the acceleration will come out negative. And maybe I'll show you that when I do the when I finish this question. Okay, so basically Ft here is going to be beating the 45. All right, so when you go to when you go to calculate your F net for number one, Ft is going to be bigger than the 45. All right, and so that's why I wrote Ft minus 45 and not the other way around. All right, now what's that got to equal? So F net equals MA. Well, which M? Because we have two of them, it's going to be M1A. All right, and so basically this first equality here, that arises from the diagram because we did a vector addition. The second equality, that's Newton's second law. Newton's second law says as soon as you found F net, okay, even if it's incomplete, like we don't know Ft, so it's an incomplete. We don't have a numerical value for it yet. But as soon as you find Ft, you can F net. I mean, as soon as you find F net, you can set that equal to Ma. Okay, so Ft, the tension, minus the 45, which is the gravity downhill, that's got to equal the acceleration on number one times the mass. All right, and so we get Ft minus 45 is going to equal M1A. That's the piece that you want to use there. And M1 is 7 kilograms, and so there's your equation for number one. Okay, for mass number one. And you can't go any further because you don't have Ft and you don't have A. But when you finish analyzing number two, you're going to get another equation in the same two unknowns, and then you'll be able to solve. All right, so the same kind of thing for M2. All right, we can look at the diagram again. You have 50 newtons downhill here, okay? And you have this tension uphill. The normal force and the perpendicular force of gravity, they cancel, so you don't have to worry about them. And the 50 newtons is going to beat Ft because it's the 10 newton that's accelerating downhill. Okay, so the 50 newton has to be bigger than Ft to get the 10 kilogram to accelerate downhill. All right, so this time we're going to write that F net for mass number two is 50 minus Ft. All right, again, the 50 has to be bigger than the Ft, and that's going to equal Ma, only in this case it's M2A. All right, so once again, this part here you got from the diagram, and that was the vector sum to give you the net force. This part here, that equality is because of Newton's second law. So as soon as you get F net, set it equal to Ma, and you can work it out. So that means that 50 minus Ft has got to equal M2 is 10 times A, and there's our second equation. All right, now what? Well, you can take the first equation here like that, and you can take the second equation there like that, and I've got them lined up, and we're going to add both left-hand sides, so we're going to have this, whoops, this plus that. Okay, so all I did was, took that and then added it to that. That's got to equal this plus that. Okay, so basically the sum of the left-hand sides must equal the sum of the right-hand sides. This doesn't always work with systems of equations, but it does here because you can see what will happen. That's positive ft, that's negative ft. So what happens is the ft's cancel, and you get negative 45 plus 50 is going to equal 7a plus 10a. That's 17a, like that. Okay, and negative 45 plus 50, that's going to be 5, is equal to 17a, like that. And then you get that a is equal to, and what's that answer? It's going to equal, and I'll put the units back in. It's going to equal, whoops, 0.029 meters per second squared. Okay, and what's the direction? Well, the direction, let's look back at the diagram. The direction is the 10 kilogram is going to be going downhill, and of course then the 7 kilogram will be dragged uphill. Okay, so we could just say here, like, my questions are multiple choice, but if I had a direction in my questions, I would say something like 10 kilogram accelerates downhill. Just say downhill, 7 kilogram uphill. Okay, like that. All right, so let me see if there's any questions in the chat. Looks like you guys are okay. Is it only 2 people are watching? Well, that's all right. I can do it. I can continue. All right. So there we go. Now, this is sufficient, but I do want to show you what would happen if you had chosen the acceleration in the other direction. So over here, if instead of A going downhill, it were uphill, and in this A here, instead of being uphill, we're downhill, what would be different? Well, what would be different is that your equations here, 1 and 2, they would actually be flipped around. So I'll just do this very quickly to show you that you would get a negative acceleration. So that's equation number 1, the way it was written right now, and this is equation number 2, the way it's written. Okay, and what would have happened is because your F net would have been in the other direction, you would have done 45 minus Ft rather than Ft minus 45 for this one. And then for this one, you would have gone Ft minus 50 rather than 50 minus Ft. Okay, so because you would have assumed that 45 is bigger than Ft. All right, now when you go ahead and you add this, so you get 45 minus Ft plus Ft minus 50, like that, on the one side. And the other side, you'd have 7 plus 10, that's 17a, like that. Notice the Ft still cancel, like that. And you would get negative 5 is equal to 17a, and then you would get that a is equal to negative 0.29 meters per second squared. So you get the same answer, but you would get the negative, and then you would go, oh, I guess then the direction in which I assumed the acceleration was going to be in, it was incorrect. And that's how you'd be able to determine that, yeah, the 10 kilogram is actually going downhill, even though you had assumed that it was going uphill. Okay, so there's a lot of ways of making sure that you can figure out which one is going to be going downhill and which one's going to be going uphill. Probably the most intuitive, without doing any calculations, is you just look at these two numbers here. Let me circle them again. There's everything else is canceling, and then Ft here is an internal force. You just compare that one with this one here, and you say, oh, gravity's pulling the 10 kilogram down one way with 50, and gravity's pulling the other one the other way with 45. Well, the 50 is going to win, and so that's why you get the acceleration in that direction. Okay, so a couple of ways in which you could figure out what the direction is. All right, so there we go. That's question number 1. Well, almost. I also asked for the tension. Okay, so I said, what's the tension in the rope? And once you've solved for A, then you can use either equation number 1 or equation number 2 to solve for T, because you know A, you plug in A, and you should get Ft out. And you say, well, which equation do I use? It doesn't matter. Both of them will give you the exact same answer. Okay, so let me actually cut and paste that here like this, and I think I've got it done both ways. So this one is using number 1, and this one over here, I didn't label it here, but this one is using number 2. If you use number 1, this is just equation number 1, and it was like 7a, but for a now I've put 0.29. Okay, and it works out to Ft is equal to 47.03 newtons. Okay, or if I use equation number 2, a here is still 0.29, like that. All right, and it turns out to be 47.1. You say, well, they're not the same. I know what's going on here is I should have kept an extra digit for that one. So it's just a round off error. But, on a multiple choice test, you would know, like if you got 47.0 and 47.1, you'd be close enough to one of my answers that you'd know which one it is. All right. So there's the first one done, assuming that there is no acceleration. Sorry, no friction. Okay, just get the acceleration. Let's do question number 2. So for question number 2, I said, you know what? Let's assume that there is friction and it's static friction, so this is not going to accelerate. And let's assume that the 7 kilogram is actually the only one that has the static friction. In other words, the 10 kilogram doesn't have any friction associated with it at all. Okay, so if we go back to this diagram here, all right, basically what I'm saying is that there's friction in here like that between the 7 kilogram and the inclined plane there. All right, and it's static friction, so that means it's not going to move. All right, so let's draw in the static frictional force there. Let me do it in red, I guess. So if the 7 kilogram wants to accelerate uphill, then the static friction has to be downhill like that. Okay, Fs. And you say, well, how do I determine how big Fs is? Well, let's start over on this side here. This time the acceleration is 0. Okay, so the acceleration is 0. So the situation you have is that these two forces cancel. All right, we've already determined that. Okay. These two forces must also cancel. Unlike the previous one, they have to cancel. And the reason is there's no acceleration up or down the hill. And so that tells you right away that the tension there is going to equal 50 newtons. All right. So unlike the previous problem where we had to actually make use of F net equals ma, here you don't have to use F net equals ma. All you have to do is basically just reason out that all the forces add up to 0 because A is equal to 0, and you immediately can arrive at the conclusion that the tension here is equal to 50 newtons. Okay, so that they cancel out. Well, if this tension is 50 newtons, then the tension over here is also 50 newtons because of Newton's third law. Okay, and if this is 50 newtons, then those two forces have to cancel these two forces here. That is the force of gravity downhill and the frictional force. Well, we have 50 newtons uphill and we only have 45 newtons downhill. And you go, well, they're not balancing out. That's right, because you need an extra 5 newtons right here. Okay, so that's the trick in getting the static friction. Static friction, unlike kinetic friction, you don't use the formula with mu s because it turns out to be an inequality. Okay, and the inequality doesn't allow you to it's actually this inequality right here, Fs divided by Fn. The inequality doesn't actually allow you to calculate mu s. It just sets a limit on mu s. So you can't use, like, even if I gave you mu s here, you can't use that to get Fs, all right? Instead, the way you get Fs is by saying, oh, well, all the forces on the 7 kilogram mass have to add up to 0. I've got 50 newtons up, and I've only got 45 down, so Fs has to be 5 newtons. If it weren't 5 newtons, then the forces up and down the plane would not cancel, and as a result, it would accelerate. Okay, so that's how you make use of that's how you get the static frictional force. All right, let's switch back to here, and let me just cut and paste the answer here, and we'll go through it. All right. All right, so we determined that the static frictional force has to be 5 newtons in order for the acceleration to be 0. All right, it has to be downhill. The other question is, what direction is it in? It has to be downhill because if you take a look at the diagram, that 5 newtons has to help the parallel component of gravity to keep this thing from being pulled uphill. If it were just a parallel component of gravity, you'd have 45 down, 50 up. The 50 up would win. So that 5 newtons extra has to be downhill to help out the 45 so that it doesn't accelerate uphill. Okay, and so that's how we determined the force of static friction. And then you can make use of the formula from US. All right, so that tells you, that answers how much static friction and the direction. Then we can make use of this, not to get the coefficient of static friction, but to get the range for the coefficient of static friction. All right, so mu s has to be bigger than Fs divided by the normal force. But this is the normal force for number 1, because only number 1, only the 7 kilogram mass has a has friction. Okay, and now at this point you say, well, I don't know the normal force. That's right. So we didn't need it for part 1, but now you do. Okay, and we found that well, not we found, but we have that the perpendicular component of gravity is m1g cosine of 45 degrees. The normal force has to exactly cancel that. So Fn1 must equal m1g cosine of 45 degrees. Okay, and so that's this equation right here. Okay, you can see it highlighted. So because the perpendicular component of gravity has to cancel the normal force, Fn1, the two must be equal to one another, and plugging in the numbers for m1g cosine theta, that's 7 times 10 times the cosine of 45 degrees, that tells you that Fn1 is 53.6 newtons. Okay, so now we have Fn1 and we have Fs, and putting it together, we find that mu s has to be bigger than 0.09328, or on a test I would round this off to 3 decibels, so, or 3 significant figures, so it's 0.0939. Okay, so let me actually write those values back into the diagram here. So we found that the normal force was 53.6. So over here, well, gravity we found to be 53.6, so this is 53.6. And because that has to exactly cancel the normal force here, that means that the normal force here was 53.6 as well. Okay, I know my diagram's getting a little bit messy, but there it is. That force there cancels that force there like that. All right, so that's what happened. All right, well, let's do the last part. And so the last part was to practice kinetic friction. So I said, well, this time assume that the 9 kilogram mass has kinetic friction of 0.03, coefficient of kinetic friction of 0.03. And I guess I didn't say this, but assume that there is no static friction for the 7 kilogram. Otherwise, this wouldn't be going anywhere. Okay, and how big is the kinetic friction, and in what direction, and what is the acceleration, and what's the tension? Okay, so basically we're repeating all of question number 1, but this time we're doing it with the assumption that the 9 kilogram actually does have some friction between it and its surface. Okay, now my diagram's gotten a little bit messy, so you know what, even though it'll take me a second, let me just redraw it. Shouldn't take that long. Okay, so over here, let me just start all over. And so this was 40 degrees here, and this was 30 degrees here, and this is the 7 kilogram mass, and this is the 10 kilogram mass, like that, and there is a string that goes across there like that. Okay, so this is 7 kilograms, and this is 10 kilograms. Okay, and let's just go through the forces again. There was the perpendicular component of gravity here and the parallel component of gravity there like that. And I'll just write in the numbers for the perpendicular component. For that one we found 53.6. So this one here was 53.6. The parallel component here turned out to be 45 newtons, like that. Okay. The normal force here, Fn1, well, it had to cancel out that 53, so it is also 53.6 newtons, like that. Okay. Now, and then there was a tension. There was a tension up here like that. And don't use the value of the tension from part A or part 1. And the reason is that it's going to be a different tension now. Okay. There's also friction, but that's on the 10 kilogram over here. Okay, so let's do the forces here. So there is force that way and that way, and the parallel component of the force we found to be 50 newtons. The perpendicular component we actually never calculated because we didn't need it, but now we do. Okay, so let me switch back over here and let me calculate the perpendicular component of gravity. All right. Okay. It turns out to be 77.9, and of course that has to cancel the normal force there, and so that's why it's equal to Fn2. All right. So let's switch back, and I can write that in there. And what was the value again? 77.9. So over here, this is going to be 77.9 newtons, like that. And the normal force here, it's not the same as this normal force, so that's why I'm going to call it Fn2. That's going to turn out to be exactly equal to this, 77.9 newtons. Okay, and then there's a tension. And I don't know the value of the tension, but whatever that tension is, it's equal to this tension over here. Okay, now this is part 1, but part 2, there's gravity. Okay, sorry, friction. And you say to yourself, which way is the friction? Well, if there were no friction, it wants to accelerate down this way. So which way does the friction have to be? The friction has to be up that way, like that. Okay, and we'll call that F subscript F for friction. Okay, and there we go. So here, for this guy, these two forces here, the tension and the friction, they are competing with the 50 Newton. But which one's winning? The 50 Newton is winning because it's accelerating downhill. Okay, if it weren't accelerating downhill, then it would at worst be stopped. Okay, in which case you're in a condition of static friction. If it is going to accelerate, then it's got to accelerate downhill. So that 50 Newton has to beat the FT and FF. All right, and so let's work out what FF is, and then we can do the net force. All right, so FF in this case, you can make use of this formula here, because for mu k, it's not the formula that relates the coefficient of kinetic friction and the force of friction. It's not an inequality. See, with an inequality like that, you can't use that inequality to solve for Fs, but here it's an equality, so you can use that to solve for FF, and that turns out to be equal to this. Okay, so we actually know that FF is equal to 2.337. Okay, if we go back to the diagram here, we can even write in, I don't know if I can squeeze it in there, but we can even write in that FF here, right there, that's equal to 2. What did I say? 2.337. 2.337, like that. Okay, so that 2.337 plus whatever FF is, they're competing with the 50 Newton, but the 50 Newton is winning. So if we write down what the net force is for number 2, it's actually equal to this. Hold on here. Okay, there we go. So the net force on number 2 is the 50 newtons downhill, which is winning, minus the FT, which is competing with it uphill, minus the force of friction, which is also uphill, and that's got to equal m2 times a, because of Newton's second law. So again, that second inequality is purely because of Newton's second law. We call that equation number 1. Okay? Now the other one, m1 equals 7 kilograms, there's nothing different between that and what we did above. Okay? So there, if we go back to the diagram, we have these two forces, the perpendicular forces, canceling against one another. So that force there cancels that force there. Okay, and we have Ft competing with the 45, and you ask yourself, well, which way is this thing accelerating? Uphill. All right, because that's accelerating downhill. So Ft has to be bigger than 45, and we have the same equation that we did before, namely that F net is going to be Ft, the winning force minus the force trying to pull it downhill. So you've got Ft minus 45, and what's that got to equal? By Newton's second law, M1 MA, but it's M1 in this case, so M1A. All right, and just cleaning that up a bit, you get that Ft minus 45 is 7A, like that, and there's your equation number 2. Now it's just a matter of solving, and so here we have, actually, you know what? Well, I can simplify this equation. Let me simplify that equation right there before I go ahead and plug in, because what I can do here is, let me get rid of the units because you know everything is in MKS. I could take the 50 minus the 2.33, all right, and that'll simplify it, and let me see what that gives us. That turns out to be this equation here. So this is a simplified version of equation number 1. Let me put that by equation number 2. Put equation number 2 underneath it here like that. Okay. And same technique. Let me add the two together. And so I've got this left-hand side plus this left-hand side. Okay. That's going to equal 10 plus 7a. So that's 17a like that. All right. Notice that the FTs will cancel. So on the next line, you just have 47.633 minus 45 is equal to 17a. And what's that going to equal? That's going to give me this. And that says that a is equal to that. Okay. So A is basically going to equal 0.15665, which on a test, again, I would round off to 3 significant figures, 0.157 meters per second squared, and that's with kinetic friction. Okay, so that answers the question, what's the acceleration? The direction, of course, is as shown in the diagram. Let me switch back very quickly. The force of friction has to be uphill at the 10 kilogram mass, okay? And the acceleration is downhill, all right? Just as a check, you can compare this with your previous acceleration here that you got without friction. And so let me see, where was that? Here it is. So this is the acceleration we got without friction. And so without friction, we got 0.29 meters per second squared. With friction, we got 0.157 meters per second squared. And that's what you would expect. The more friction there is, the less it's going to accelerate, because the friction is slowing down the acceleration. Okay, and so it's not a perfect check, but you know, if you had made a numerical error in there, you would have noticed, you know, if you've got a number here that was bigger than 0.29, you would say to yourself, well, wait a second, how's that possible? How's it possible that with more friction, it's going to accelerate faster rather than slower? And so it doesn't. Okay. All right. So next, I asked for the tension. What's the tension? And for this one, you can choose either equation and just plug into it. And so I guess I'm going to use equation number 2 here. So there we go. We'll just, to solve for FT, just substitute into 1 or 2. Okay. And I decided to use, I guess, equation number 2 here. Okay. So FT, so this is equation number 2. All right. So FT is going to equal 7a plus 45, just bringing the 45 to the other side. Substitute in for the acceleration because we know it now. And that gives us 46.1 newtons. Okay, so with friction, you've got 46.1. And you'd expect that, you know, because you've got, let's go back to the diagram, you can see how you can reason this out. Because, say, take a look at the 7 kilogram, because that's going to accelerate less, FT has to be less than it was in part A, okay, or part 1. Okay, it's the first question. You know, if FT is smaller, then the 7 kilogram will accelerate less. And that's what you have here. Because the 7 kilogram is accelerating less, 0.157 rather than 0.29, the tension is less when there's friction than it is when there isn't friction. Okay, so there you go. There's a slightly different variation on what we've done before. Previously, we just had like one inclined plane and then a mass dangling off of the side. But this time I said, you know what, let's do two inclined planes. It's not that much different. All you have is that basically instead of just pure gravity on one side, you actually have to have a parallel and perpendicular component for both of the masses that are on the on inclined planes. Okay, so let me take a look in the chat here and see if there's any questions. Doesn't look like it. So if we'll end a little bit early. If there are no questions, then I'll just say goodbye. And if you have questions, of course, you can catch me on my usual evening Google Hangouts. All right, guys. Bye-bye.